This is another chemical equilibrium problem. In this case, we use approximations, and you will see what we mean. We use approximations to simplify the problem instead of using the quadratic equation like you saw in the last problem. So let us use the example that we have here. Dihydrogen sulfide is in equilibrium with hydrogen and sulfur gas. We are given the Kc as shown here, 1.67 times 10 to the power negative 7 at 800 degrees Celsius. So initially this reaction had 0.0250 molar of dihydrogen sulfide. So what we want to do is to determine the equilibrium concentration of hydrogen and sulfur gas. So that's what we want to do. So let me write this equation again. We have two H2S gas in equilibrium with 2 H2 gas plus S2 gas, and we are given the Kc of this reaction as 1.67 times 10 to the power negative 7. So we are given the initial concentration of sulfur. So initial of dihydrogen sulfide as 0.0250 molar, and we need to find the concentration of hydrogen and sulfur at equilibrium. So this is our problem. So to solve this problem, because we know that we have the initial concentration for dihydrogen sulfide, and we know from the reaction equation to get to an equilibrium, the dihydrogen sulfide must lose a certain concentration that we are going to call X. So the hydrogen sulfide loses a certain amount of X, and then hydrogen will gain the same amount of X, and sulfur will also gain some X. So let's see how it works. So I'll just say let the change in concentration be X. So I'm going to have the ICE table, ICE table. So remember, ICE is initial, change, and equilibrium concentration. So we have three of these. So let me just get rid of this one here. Yeah, actually I was correct here. Then I'll have this one, this line. Yeah, the line is just disappearing. And then this line. So my concentration of the reactant here, the concentration of the first product, the concentration of the second product. So the initial for this one, as we can see from here, is 0.0250. But at the beginning, we did not have hydrogen and we did not have oxygen. So both of them will have an initial concentration of 0.00. This one also 0.000 molar. Then we talk about what is the change in their concentration. We said that let X be the change in concentration. But if you look at this equation, or if you look at this species here, we have 2 dihydrogen sulfide, which means this is losing 2 of that X. And here we also have 2 hydrogen. But this is the hydrogen sulfide is a reactant and it is losing the X. That's why we have negative 2X here. Hydrogen is a product. In this case, it is gaining. So because of the 2 here, it is going to gain 2X. Sulfur is also gaining, but there's only 1 sulfur. So that one is going to gain X. So what would be the equilibrium concentration? I'll just say equilibrium concentration. The final will be this one minus this. So 0.0250 minus 2X. That will be the equilibrium concentration of dihydrogen sulfide, while the concentration of hydrogen will just be 2X, and the concentration of sulfur will just be X. Now, once we do that, we come back to our equation up here. then we'll say Kc Kc will be equal to the concentration of hydrogen squared, the concentration of sulfur divided by the concentration of dihydrogen sulfide squared. But we know that these are our concentration. So up here we have the concentration of hydrogen squared. We know the concentration of hydrogen from the table is 2x. That is, the equilibrium concentration of hydrogen is 2x. But now we put all this squared. While the concentration of sulfur is just x. So x down here. The concentration of dihydrogen sulfide is 0.025 minus 2x, and all this we put it in, we square it. Now once we do that, we need to make an assumption. So I can just simplify this one a little bit. 2 squared is 4. X squared here will be x squared times x. So x squared times x will be x cubed. So this one divided by 0.025 minus 2x squared. Now I'll create a space here so that I can continue solving it this side. Now at this point we make an assumption. We assume that x is very, very small. So assume x is very small. So why are we assuming that? If you assume that x is small, you can ignore it in the denominator. So we can ignore x in the denominator. So this one becomes 4x3. Let me just put the whole thing. 0.025 minus 2x squared becomes 4x3 divided by 0.025 squared, and this is equal to k C. So in that case, we already know that this is our Kc. So we can say 4x cubed divided by 0.025 squared is equal to 1.67 times 10 to the power negative 7. So if you play around with it, 4x3 will be equal to 1.67 times 10 negative 7. This one times 0.025 squared. So once we do that, we find that this is 1.044 times 10 to the power negative 10. Now I'll write that again. 4x3 is equal to 1.044 times 10 to the power negative 10. This means that x3 is equal to 1.044 times 10 to the power negative 10 divided by 4. So to find x, you need to determine the cube root. The cube root of 1.044 times 10 to the power negative 10 divided by 4. Once you get the cube root, x is going to be 2.97 times 10 to the power negative 4 molar. So that is our change in concentration. That is our x. Now, we used an approximation. So we used an approximation. In that approximation, we said that x is very small. We said x is very small. That's what we said. But how small is x? So to determine how small x is, we use 5% rule. So what does the rule say? If x is less than 5% of our initial concentration. The approximation is correct. So the approximation is correct. Now, if this concentration is more than 5%, then our approximation is not correct. We should use the quadratic equation. So if X is greater than 5%, approximation is not correct. In that case, use quadratic equation to solve for X. Now, this result here, we need to find out if it is 5% of the original solution. So how do I do that? Let me create space here to solve that problem there. Our original solution, So our original solution was 0.0250 molar. That's our original solution. Our X is 2.97 times 10 to the power minus 4 molar. Now we'll take this X as a percentage of this and find out if it's less or more than 5%. So what do I do? So what I'm doing is X divided by 0.0250 times 100%. So the X is 2.97 times 10 to the power negative 4 divided by 0.0250 times 100%. For that, our answer is 1.19%. So this is less than 5%. So what does the rule say? If X is less than 5% of the initial concentration, the approximation is correct. So what does it mean? It means us saying that X is small was correct. So I will say here, our approximation was correct. So that's how we solve this problem. This is our X, and here we are just testing if the approximation was correct, and we see that our approximation is correct, since 1.19% is less than 5% of the initial concentration. There are some quick ways that you can determine that in this case I don't need to use the quadratic equation, or in this case I am going to use the quadratic equation because x is big enough. So, just as a reminder, if x is big enough, then use quadratic equation. So if x is very small, use approximation. So there are some ways that you can just look at a problem and say, in this case, the approximation is going to work. For example, if you are given a concentration, so let's say a concentration of something is A is equal to 0.500 molar, and you are given Kc is equal to 1.25 times 10 to the power negative 5. You see that the Kc is very small in relation to your concentration. Kc is too small in relation to concentration. In that case, the approximation may work, because you look at it and say, you know what, this is too big. If the Kc is this small, it means the x will really be small, that is not going to change anything about this one. So what do we mean? What we mean is, let's say, based on what we have here, let's say x is equal to 0.002. So x is equal to 0.002. Let's say if this is going to change the A, to change this A that much. So let's take 0.500 minus x, which is 0.500 minus 0.002. So that gives us 0.498, which is approximately 0.500. So if you have a Kc that is small, that is too small, it will give you like a very small x, such that when you subtract that x from the original concentration, it won't change much. It won't change your math that much. Now, let's suppose, using the same problem, let's suppose the initial concentration has changed. The initial concentration A in this case is equal to 0.050 molar. And the Kc is the same. Kc is equal to 1.25 times 10 to the power negative 5. And let's say that our x is also the same, that it did not change. X is equal to 0.002 molar. So I'll add molar there. If we do the subtraction again, A at equilibrium will be equal to 0.050 molar minus 0.002 molar. And that gives us that will give us 0.048 molar as our final concentration. So this is still small. As you can see, no big change. Still very small. Now let's keep on reducing the concentration. So let's take A is equal to 0.007. That is our initial concentration. And our X is still 0.002 molar. Now in this case, if you make a subtraction, the A at equilibrium will be equal to 0.007, that is our initial, minus 0.002, that is the change in that concentration. In that case, the difference so the equilibrium concentration will be 0.005. Now if you take this as a percentage of this, you will see that it is bigger than 5%. So 0.002 divided by 0.007 times 100%. I mean, if you take the percentage of this versus the percentage of this, not this one. So it becomes 29%. So what does it mean? It means you need to look at the concentration and your Kc. If the concentration is as small or is small, if the initial concentration is small compared to the Kc, then definitely the approximation will not work. But if the initial concentration is big in relation to the Kc, then the approximation will most of the times work. So if we say my A is 0.500 and Kc is 1.2 times 10 5, you can see that this is to 1 decimal point, this is to 5 decimal points. So there is a huge difference. The concentration is way bigger than the Kc. So this one approximation works. But if you take, if A is 0.007 and then Kc is the same, 1.2 times 10 to the 5, you can see that this is the approximation itself is 10 to the negative 3 and the Kc is 10 to the negative 5. That is not different in terms of their, that is not very different in terms of their magnitude. So in this case, approximation probably not work. So most of the problems that we will solve in this class will be based on the approximation. So take note of that. Thank you.